Hi, in this video, I'm going to talk about quality of service mechanisms. Uh, so quality of service, all right, or lack of quality of service, okay, is once the QoS requirements of the network have been defined, an appropriate service model must be selected. So the service model is just a kind of a design philosophy on how to approach quality of service. There's three service models to choose from. Best effort, which is pretty much, do what you can and without any kind of quality of service mechanisms. There's an integrated services model and a differentiated services model. So let's take a look at these. Best effort, okay? Best effort is the application is going to send data whenever it wants in any quantity it wants, without requesting any permission or informing the network. No real quality of service here, okay? And basically, first in, first out, okay? Okay, so with best effort, the network's going to deliver the data without any assurance of reliability or delay, okay, or throughput. It's not looking at any of these. Of course, the transport protocol, TCP, may be concerned about that at both ends, but the network itself is not going to be concerned about this. Okay, so best effort. This would be like a fire truck having to wait in normal traffic lanes along with everybody else. There's no priority, just kind of a best effort. All right, another model is known as the integrated services model. This is where the application actually requests specific kind of service from the network resources, okay? In the Cisco INSERV model, it uses something called RSVP, Resource Reservation Protocol. Now, let me kind of just say here, this is something that has never really taken off. And we'll see why. We actually have more scalable ways to do this. It's used by applications, basically signal the devices from end to end saying, hey, I have certain quality of service requirements. This was adapted from the old telephone network philosophy on how to handle things. And the problem is it's not very scalable and requires continuous signaling from the network devices. So it would be like the fire truck radioing ahead to every intersection before it leaves the firehouse and saying, hey, I'm coming. When I get there, I need priority. Okay. The differentiated services model is different, okay? It enforces or applies these QoS mechanisms on a hop-by-hop basis, okay, uniformly. Okay, and this is going to provide both flexibility and scalability. And we'll see how this works. This is with, well, let's go through this and we'll see how it works. Each device is configured with QoS policies to follow, so they all have policies, okay? But they're not being informed ahead of time about any kind of device, about the packets that are coming. No advanced reservations. Okay, it will handle it on a packet by packet basis. Okay, so the QoS information is actually contained in the packet header. Okay, so where INSERV uses a connection-oriented approach, basically informing all the devices ahead of time, the whole, knowing what the path is from source to destination and what that connection is, that virtual circuit, let's call it, and having to inform all the devices along the way about its QoS policies. That's the INSERV approach. The differentiated services approach says, I'm not worried about that, okay? Fire truck analogy would be the police at each intersection, or you have a special traffic light, or just the sirens and the flashing lights on the fire truck. Everybody sees it's coming, and as the fire truck passes through the lanes and at the intersection, everybody pulls over and stops. Okay, so the quality of service mechanism is the fire truck itself, or part of the fire truck. Okay, that said, we have in IPv4 and IPv6 headers, we have the type of service and the traffic class to provide this. Let's take a look at, I'm just going to use the IPv4 header here, type of service here. But so in differentiated services architecture, the quality of service information is contained in the header itself. Each packet is classified before being entered onto the network. So the application is going to put what the quality of service needs are before that packet enters the network. Okay, so let's using the type of service field in IPv4, and by the way, this is the same in IPv6. It has IP precedence, and this is spelled with an S here because I think I grabbed this from an English version of this. But anyway, IP precedence or the DSCP, and we're going to take a look at both of these. So you can see, and this is for both IPv4 and IPv6. Okay, so we can use IP precedence, in which you notice there's 3 bits used here, or the DSCP, which actually uses 6 bits. Okay, so once these packets are classified at the edge, now this can be by the sending device itself, the application, or it could be actually an edge device, a switch or a router before it goes on to further networks. So this can be classified by the device itself, or access layer switches, border routers, or the host or an application itself. Okay. And this does not require network applications to be QoS aware. So the application itself doesn't have to be QoS aware. You can actually handle this at the access layer switch, or like it shows here, a border router. Okay, so the type of service byte has IP precedence, 3 bits, and 5 bits are unused, or the DSCP, diff serve code point, known as the DS byte. Okay, so TOS byte equals DS byte. You're going to hear those interchangeably. Okay, same location, but different interpretation. And I'm going to talk more about this, more than what the curriculum goes into. So let's kind of go into this a little bit more. Type of service. So if DSCP is the first 6 bits, as we can see here, and the IP precedence is 3 bits. And they cannot be used simultaneously. Okay, you're going to use one or the other. Okay, if DSCP is used, it will supersede the IP precedence. Now the difference is, with IP precedence, you have 3 bits, so you have 8 possibilities, 8 different classifications. Using 6 bits, that gives you 64 different possibilities. All right, so that's at the layer 3. What about layer 2? Okay, and I'm going to bring all this together in just a moment. Okay, an Ethernet frame has no fields for QoS. Okay, but when we sent them over a trunk link, okay, there is a VLAN tag, and we've taken a look in previous videos when we talked about the VLAN and the VLAN ID. There's also a user priority, 3 bits. Yep. And we can see how those 3 bits are classified here. Okay, so we have class, it's called class of service. Okay, from 0, which is best effort, okay, to 1, which is medium, 2 high, 3 call signaling, 4 video conferencing, and then 5 voice bearer. So there's actually 5 different classes, with 5 being like for a voice conversation. Okay. All right, so the 3-bit class of service field allows 8 levels of priority. Does that sound familiar? 8 levels of priority, kind of like the IP precedence, right? we're going to bring all this together in a moment. Okay. So switches, so, if you have a device like a layer 2 switch that cannot look at the IP header because it's a layer 2 device. There are layer 2 switches that can look at the IP header for quality of service, but let's say you have a layer 2 device that cannot, that it can only affect the class of service, the layer 2 frame, the VLAN tag, then those devices are going to need to use the class of service in the Ethernet header as opposed to the IP header for affecting any kind of quality of service. We'll talk more about this here in a moment. Okay, and also the host applications can also set that class of service. Now routers can translate this cost of service into the equivalent IP precedence or DSCP value. And we're going to bring all this together in a moment. Okay. All right. So trusting the class of service, it's up to the edge device. Must decide whether or not to. So if the host has changed the class of service, the sending host says, this is what I want the class of service to be. Then the switch can choose either to trust that or not to trust that. And we get into this when we start talking about voice over IP, when you have an IP phone connected to your layer 2 switch. That's really where this comes in. Okay, and this is what we call trust boundaries. Okay, so where do we trust this information, trust the quality, the class of service? Okay, do you trust it at the, where are you going to mark it and where are you going to trust it? Where are you going to mark the class of service, and is that device going to trust what that marking is? We call that the trust boundary. Okay. So, and it just depends what kind of device you have there and whether you trust, and you'd be configuring these switches or multi-layer switches or routers to trust or not trust the class of service or the type of service, if it's IP, or disregard it. All right. So let's talk about these layer 2 markings, because the decision whether or not to classify the quality of service at layer 2 or layer 3 is not trivial. This is kind of beyond the scope of this presentation, but you do layer 2. When would you classify it at layer 2, give it the traffic a priority, whether you do that at the host or the switch? Again, that's a separate decision, but you'd have to do it for any non-IP traffic. Okay, if it's not IP, then you're going to have to classify it at layer 2. If the switches are not IP aware. So if you're doing the classification, or you want it to look at the classification, if the switch cannot look at the type of service byte here in the IP header, then you're going to have to use the layer 2 marking. Okay. Now the nice thing about layer 3 marking is it will carry it from end to end, so it will live with the packet. Okay, let's just talk about how we map these. And I'm going to show you how all of this works in just a moment. So notice that we have here in layer 2, the VLAN tag, we had a user priority 3 bits, okay, class of service. And we have 0 through 7 looking at all 3 bits. The DSCP, it maps. There's a mapping between the DSCP and IP precedence to the class of service. So whichever one you're using, they actually mean the same thing. We can actually take the information from the VLAN tag user priority and use that in the, copy that into the type of service header, or the IP header, the type of service byte, and vice versa. Let's take a look at how we do this. Okay, so I put this chart together to kind of bring it all together. We have IP precedence, which is really only 3 bits, right? We have DSCP, which is 6 bits. And up here, I'm showing the kind of the mapping with the class of service. But over here, we have class of service here, okay? And you're gonna see some of these terms sometimes. So this is well, way beyond the scope of what you needed for this chapter. But let's take a look at how this works. So routine traffic, okay, this is no class of service. Default class 0, this is best effort, okay? If we look at the IP precedence, okay, there's 3 bits. There's 0, 0, 0. That's a value of 0. Whoops. Okay. The DSCP is also, remember it's 6 bits? Well, those first 3 bits match the same first 3 bits of the IP precedence. They would be the same. And of course, class of service, 3 bits, is also 0. So they're all the same, whether we're talking IP precedence, DSCP, or layer 2 class of service. Okay. Now, classes 1 through 4 here, these are known as assured forwarding levels. And sometimes when you're reading articles or information or anything on quality of service, they talk about things like it's class AF11 or AF12 or AF13. So, so let me just talk a little bit about these. So they're called assured forwarding levels, okay? They map to, in IP precedence, the priority, intermediate, flash, and flash override. Okay, so if we see here, we have beyond the routine. Okay, now we're going to get into the higher priority levels. Okay, we have IP precedence. Let's see here, let me just kind of go through these. There we go. First 3 bits is 0, 0, 1. That maps to the priority 1, 0, 0, 1. That's a 1, right? Well, in DSCP, the first 3 bits are also 0, 0, 1. Okay. Now you can see we have 3 groups here. Okay. But we'll get there in just a moment. In intermediate 2, the 0, 1, 0, that's a 2. That maps to AF2, which is 0, 1, 0 in the first 3 bits of the DSCP. One more, let's look at one more here. Flash, IP precedence, 3, that's 0, 1, 1. That maps to AF3, which is 0, 1, 1, the first 3 bits. Now notice the class of service is also 1, 2, 3, just like the IP precedence, 1, 2, 3. And of course there's 4 as well. Okay, there's also a class 5, which is known as expedited forwarding. Okay, that's actually reserved for premium service things, time critical traffic such as voice. Okay, would be IP precedence 5, DSCP EF, okay, or class of service 5. So they all map IP precedence, DSCP, and class of service, the layer 2. Okay, classes 6 and 7, these are reserved for things like sending protocol information, STP, those kinds of things that we need the traffic to get there. That's the most important, because if the control traffic doesn't make it, then none of this other stuff's going to work. Okay, so notice in DSCP though, we have another 3 levels for each class. Low, medium, high. Okay, that's known as the drop precedence. Okay, so low meaning least, so within this class. So this is where we can further more granular and more granularity be able to have specific classes. So we have low, medium, and high in each. Low means least likely to be dropped. High means more likely to be dropped. So it doesn't mean higher priority. It actually means lower priority. Just this is drop precedence. Low gets a higher priority. It's least likely to be dropped. high, more likely to be dropped. Okay. So this just gives us more granularity in each one of these DSCP classes. And that's what differentiates DSCP from IP precedence and class of service, is that we get these 3 more in each. Okay, so this is where we get these code points. Okay, so we have the first 2 letters is AF or EF, followed by the class selector number. So this is like, you know, this is where we have the same 2, AF2, same as the IP precedence and same as the class of service, okay? But the next one provides the drop precedence, the 1, 2, or 3 following it, low, medium, or high. So you'll notice each one has 1, 2, 3 following the class. AF, and then the class, and then the drop precedence. Okay, and this is looking at it in binary. Okay, and I mentioned this because sometimes you're going to see the DSCP values, they'll say AF21 or they'll say 18, depending on whatever you're looking at. All right, so hopefully these don't look as random as they seem. So there's the 1, there's the 2, there's the 3. Okay. And then the drop precedence, 1, 2, 3, looking at it in binary. Okay. So this is just, and this is just the decimal value of what we're looking at here. Okay. So like 18 here is 16 plus 2. That's where they get the 18. Or we can look at it as AF21, AF2, okay, okay, and then low, medium, high. Yeah, I know, a little strange. Okay. Anyway, this is where where all this mapping comes in. So we have a class of service 0 and a DSCP value of 0. Okay, so this is how all this stuff matches. 2 matches to a IP precedence of 2, but 16. So if this was all zeros here, 0, 1, 0, followed by all zeros, that would be 16. Okay. All right. So there are congestion avoidance tools to help us monitor traffic, and you know, it's better to anticipate whether congestion is going to happen so we can find ways to avoid it. And that's actually done through dropping packets ahead of time. Okay, it's better to drop a few packets now than to be dropping a lot of packets later. Okay, so Cisco uses something called weighted random early detection, okay, to help avoid congestion. We're going to take a look at this in a moment. It's an algorithm, a congestion avoidance algorithm that drops packets ahead of time, allows TCP traffic to decrease, throttle back before all the resources become just full or totally exhausted. Let's get into this here. Okay, so tail drops. Okay, so what we want to do is avoid any kind of long-term or large congestion. Okay, so we do have techniques for queuing, okay, but we'll need to be drop some packets. Okay, so it says, hey, now there are more packets than I can store in my output buffer, and I can't send them out fast enough. Guess I have to start dropping later packets until I have enough room. Okay, so a traditional strategy is the tail drop. What tail drop is a router simply discards any of the later packets coming in. Okay, discards any packet that arrives at the tail end of the queue that has completely used up its packet holding resources. It says, I can't hold any more packets. I need to start dropping them. Okay. This is the default queuing response to congestion. Okay, I'm congested, I can't handle any more packets, drop everything that's coming in now. Okay, and tail drop, this dropping packets, just whatever you can't handle in your buffers, does not differentiate between classes of service because there's no room in memory, no room in the buffer, no room to take those packets in and classify them. So what happens with TCP is when that happens, the hosts that experience this go into TCP slow start. Okay, it says, oh, I'm not receiving the TCP acknowledgements like I expect. Probably some kind of congestion. It means I need to lower my, change my window size to a much lower value, meaning I'm going to send fewer bytes and I'm going to wait for an acknowledgement because there's some congestion. So I'm not going to send a bunch of packets. I'm not going to have a big window size like I did have. Send a bunch of packets and then and just get those acknowledgements fairly quickly, and I can just keep on sending. I'm sending those and I'm not getting the acknowledgements. They're timing out. There must be congestion. They must be getting dropped. So I'm going to slow down. I'm just going to send a fewer number of bytes, and I'm going to wait and let the network kind of tell me, yeah, I'm getting these now. Then we'll pick up speed. I'll send more and more and more. I'll increase my window size as those acknowledgements are more consistent in coming back from the other end. That tells me that the network is okay now. All right. So so what happens is when everybody does that, there's very little traffic that needs to be sent out the interface. So what happens with this is this. Traffic flows and enters the queue at different times. Okay. So what we see here is that we see a lot of devices sending, okay, and then the queue is overused. So all these devices are sending, and then they have to all together say, oh, wait a minute, I'm not getting the acknowledgements. The router's dropping packets, not just for you, but for everybody. So they all then lower their window sizes and then do the slow start again. And then what happens is you can see that everybody's slow start and window sizes become synchronized because everybody's experiencing the congestion at the same time. All the end devices. So everybody's getting synced. So this is not a good way to handle things because if you look at it, everybody's doing fine. And up here, everybody's fine. Okay. But then there's congestion and everybody has to then go to slow start and start with the smaller window sizes, wait for the acknowledgements before they start increasing their window sizes, sending more and more packets. Okay. And we can see down here, this is when the router says, hey, there's not as much traffic. And then up here, so it goes between experiencing little congestion to experiencing a lot of congestion, or no congestion, I should say. No congestion, having plenty of bandwidth, underutilized to being overutilized, underutilized, overutilized, underutilized, overutilized. Not just the routers, but also the network and also the hosts, okay? All right, this is called global synchronization. And this occurs when multiple TCP hosts, which is common, reduce their transmission rates in response to packet dropping, and then increase their transmission rates after the congestion is reduced. Okay, so as we can see, it's waves of underutilized and overutilized resources. Okay. So what we use is something called weighted random early detection. Okay, and the idea here is that my buffer is not full, but I am going to use random early detection, RED. We'll talk about the weighted in a moment, and start dropping some packets now to keep that global synchronization problem from happening. So not all of these devices experience that all their packets are, being dropped, or, when there is congestion, but some will see some packets dropped, but not have to fall all the way back to slow start, the TCP slow start. Maybe just change their window size slightly, maybe not at all. Okay, but basically we're avoiding congestion. We're dropping some ahead of time while the buffer is not full. Okay, so this is to prevent those tail drops from everybody going into slow start. Okay, so weighted random early detection, okay, just extends these functions by permitting more granular red drop profiles. So I'm not going to get into what those profiles look like, but it combines IP precedence, or the DSCP code point values are used. There's also some different thresholds, minimum and maximum thresholds you can set on the devices for buffers and things like that. So anyways, these are all mechanisms we use to avoid congestion. But then when there is congestion, we also have some, quality of service mechanisms within the router to handle it. All right, so that's a little bit on QoS mechanisms. I hope that helped, introduce you to some of these concepts.